Okay, so today we are going to look at Chapter 9, Section 7, which is going to be sample space, probability, independent and dependent events, and then disjoint and overlapping events as well. So let's get started first. And a lot of this today should be fairly review. We did something very similar last year in Algebra 2. So we're going to look at sample space first, which is basically just a list of all the possible things that can happen. So if you flip two coins at the same time, what's the sample space? Well, what could possibly happen? So if we have our sample space, we could have that you could have a heads and a heads. You could have a heads and a tails. You could have a tails and a tails, or you could have a tails and heads. And if you are going to list this out for WebAssign, WebAssign is going to ask for set notation. Set notation just means that you are going to use that fancy little squiggle, and you're just inside of the set, you're going to list the possibilities. So you're going to have heads, 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 tails, just separating them with a comma, tails, tails, or tails, heads, like that. So you're going to basically put it inside of a set of brackets. And then what is the probability that you get but tails on both? Well, there is 4 possible things in your sample space, and there is only one of them that has both of them are tails. So it would be 1/4, and I believe everything in your WebAssign today is going to want simplified fractions. Okay, so if you have 3 children, what is the sample space? Okay, well, let's list them out. Let's go ahead and put that list in set notation. We could have 3 boys. We could have 2 boys and then a girl. We could have a boy, girl, boy. A boy and then a girl and a girl. 3 girls. 2 girls and then a boy. A girl, then a boy, then a girl. Or we could have a girl and then 2 boys. And we're going to just put that in our set notation. So then if we wanted the probability out of 8, there's 8 possible ways you could have 3 children. How many would be at least 2 boys? There, if you count them, you've got 1, 2, 3, 4 ways that you could have at least 2 boys, which would be 4 out of 8, or 1/2. What is the probability of drawing an ace from a standard deck of cards? Well, our sample space is all the cards in the deck, which is 52, and there are 4 aces, which means 4 out of 52. Simplified would be 1/13. Okay, let's just look at a couple other quick examples. When you're listing sample space, I would not probably ever have you list a sample space that has more than probably maybe 10 things in it that you'd have to list. When you roll 2 die, 2 6-sided dice, there's 36 possibilities. So if you ever are going to need to use something like that, I would actually provide you with a sample space and then you would just analyze it. So if we want to know the probability of rolling a sum of 7, well, there are 36 possibilities. Sum means that we are going to add our 2 dice together to see what we get for a sum. And if we want a sum of 7, we would be in this diagonal right here. And there are 6 ways that you can do that. So you'd have 6 out of 36, or 1/6. Okay, what is the probability your roll will be a prime number? Prime numbers, remember, are not 1 is not prime, but prime would be anything greater than that. So let's see here, I was going to erase my stuff here. Then all of our sums, if you look, the lowest sum that we're going to have is 2 if you rolled a 1 and a 1. The highest sum that we would have would be 12 if you rolled a pair of 6s. Between 1 and 12, our prime numbers are going to be 2, 3, 4 is not prime, 5, 6 is not prime, 7, 8's not prime, 9's not prime, 10's not prime, or 11. So if you look up here in your chart, you would have sums of 2, the sum of 2, that would be this one. 3 would be this one or this one. 5 would be this diagonal here. 7, again, would be that diagonal going across the middle here. And then 11 would be these 2 here. And if you count them all up, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 ways out of 36 where you would end up with a sum that is prime. So 15 out of 36 can simplify to 5/12. Our next topic is going to be independent and dependent events. Okay, so we're going to talk about independent and dependent, and then we are also going to talk about mutually exclusive and disjoint. And so we need to know the difference. So the easiest way to explain independent and dependent is we're going to call it the multiplication rule, which means we are going to multiply our probabilities together, okay? And we are also going to have multiple events. It's going to be more than one thing going on. So we're going to multiply our events together. So examples of independent would be pulling a card from a deck of cards and putting it back before you pull the next card, so there's still the same number of cards in the deck. Taking a marble from a bag, putting it back before the next marble. Again, the key a lot of times is you put back what you take out, so there's still the same number of options in the bag or in the deck. Or if the two things have nothing to do with each other at all, then you just multiply the two probabilities together anyway. So we've got an example here. Let's go down to our first example. A student's name is chosen. There's 20 kids in a class. If you randomly choose 3 times, what's the chance that Braden's name is going to be chosen 3 times? Well, the first time I pull a name, I've got 1 Braden in the class. We're going to assume there's only 1 out of 20. The second time, there's still only 20 names in my class because I can pick the same name twice. So I'd have 1 out of 20 and 1 out of 20, which is going to be 1 out of 8,000. Not very likely that I pull the same name 3 times in a row. And then we do the same thing with numbers. If I put the piece of paper or whatever it happens to be back each time, and I want to know the sums are less than or equal to 5, which means those possibilities are 1, 2, 3, 4, or 5. And so that means there are 5 possibilities out of 20. The second time is still going to be 5 out of 20 and 5 out of 20, which would be 125 out of 8,000. A little more likely to have a number less, 5 or less, than it is to just have one specific number that you're looking for. If you want to try this next one, you go ahead and try that, but I did 2 examples, so we're going to move on. Dependent events means whatever happens first is going to impact what happens next. So a lot of times what you'll see is you'll pick a card out of a deck, you'll pick a marble out of a bag, you'll do something like that and not put it back, which means the second time you go to choose, there's going to be 1 less item in the sample space. So if you draw 3 cards from a deck of 52 cards, you do not return the cards each time before you pick. What's the probability that you draw an ace, a spade, then a face card? And we are going to assume that you don't get the ace of spades the first time. We're just going to assume each time there's just 1 card less in the deck. So we have the probability of an ace. Well, there are 4 aces out of 52. Okay, the next time, since I did not put that card back into the pile, now I no longer have 52 cards. Now I only have 51, and I'm saying I want to know about a spade. There are 13 spades, and then a face card. Face cards are Jack, Queen, King, and now instead of 51, now there are only 50 because I have 1 less card because I did not return it. So what I got the first time is going to impact what I get the second time. And there are 12 face cards, and if we multiply them all out, we get 624 out of 132, 600. So not very likely that that would happen. And again, you have a bag of marbles that contain 2 blue, 5 red, and 3 orange. You are going to choose 3 marbles without putting the marbles back in the bag before choose them. So what's the probability you get a blue, then an orange, then a red? So a blue, well, there are 10. So there are 2 out of 10 that are blue. Well, now we only have 9 in our bag. In the orange, there's 3 orange, and then now we only have 8 left in the bag. We want to choose a red, and there are 5 red. So we have 6 times 5, which would be 30 out of 720, which would simplify to 1/24. Just a reminder that your calculator can simplify fractions for you if need be. Okay, this time we're going to look at disjoint mutually exclusive and disjoint is the same thing. So disjoint and overlapping, we're going to call this our addition and subtraction rule. And this means that you are looking at one single event that can't happen at the same time. Okay, so like drawing one card from a deck and it's a spade and a heart. It can't be both of those. It can't both be a spade and a heart. Flipping one coin and it is both heads and tails. So what we're going to do is we are going to just add those two probabilities together. Remember, this is one single event. We are not looking at drawing two cards, three cards, anything like that. We are just looking at one card and that's it. So what is the probability of rolling a die one time and getting an even number or an odd number? Okay, well, what's the probability of getting an even number? Well, even numbers are 2, 4, and 6. There are 3 of them out of 6. Plus, we're going to add odd number, which is also 3 out of 6. So you have a 1 out of 1, which is guaranteed you will get either an odd or an even number. Probability of picking a card from a standard deck and getting a 3 or a face card. Well, the probability of a 3, there are 4 of them out of 52. A face card, there are 12 out of 52. And we add them together to get 16 out of 52, which is going to simplify to be 4 out of 13. Again, we can just leave these as simplified fractions. Last one, probability of the ace of hearts or a spade. Okay, so the ace of hearts, there's 4 aces, but there's only 1 ace of hearts out of the 52. Spades, there are 13 spades out of 52, and we're just going to add them together, add our numerators together, denominator stays the same. So we'd have 14 out of 52 or 7 out of 26. The other way to think about it is what's called overlapping, which means that single event could have something in common. Like the two things that you're looking for could have something in common. So like you pick a card from a standard deck and it's a spade or a 7. Well, you have spades and you have a 7, but you also have the 7 of spades. And when you're counting these, you can't count them twice. So if you count the 7 as a 7 of spades and then you also count the 7 of spades twice, you have to subtract it back out. So what that means is this formula right here, okay? Probability of A or B is you're just going to add together your probabilities and subtract out whatever they have in common. So for example, what is the probability of drawing one card from a standard deck and selecting a heart or a face card? Okay, well, the probability of a heart, remember how many hearts are there in a standard deck of cards? There are 13, so we'd have hearts would be 13 out of 52. A face card, there are 12 out of 52. But we can't count those heart face cards twice. So you would be counting the Jack of Hearts, Queen of Hearts, and King of Hearts twice if you didn't subtract out the overlap. Those 3 cards are part of both of those. So you'd have to subtract out 3 out of 52 because that would be representing the Jack of Hearts, the Queen of Hearts, and the King of Hearts. And if we add our numerators together, we would get 22, and then our denominator is 52, which simplifies to 11/26. And then last, what is the probability of a 4 or a spade? Well, our probability of a 4, there's 4 out of 52, plus our probability of a spade, there's 13 spades out of 52. Well, how many do they have in common? Well, there's the 4 of spades that you counted as both a 4 and a spade that you would have to subtract out. There's 1 of them that you would have to subtract back out, which would give you 16 out of 52. And to simplify, that would be 4 out of 13. Okay, last thing, what is the probability of drawing a black card or a face card? Okay, and I know that there are black cards that are also face cards, so I know I'm going to have some stuff to subtract back out. A black card, there are 13, no, not 13. We're talking about spades and clubs, excuse me. We're talking about spades and clubs. Let me actually get the right number. Spades and clubs are both black, which means there are 13 plus 13 more. So there are 26 black cards out of 52. Half the deck is black. A face card, any face card, okay, there are 12 of them. There are 3 in each suit. So there would be 12 out of 52. And then how many are both black and a face card? Well, the spades have the jack of spades, queen of spades, and king of spades. The clubs have the jack of clubs, queen of clubs, and king of clubs, which would be 6 total out of 52. And if you add those together, you would get 32 out of 52. Simplified would be 8 out of 13. Okay, so these examples here, when they have something in common, you have to subtract out the overlap. This last slide is just in case you need a reference point. There's no problems that go along with this right now. This is just if you aren't sure about cards. There's the 4 suits, what they look like, how many are in each suit, all that kind of stuff. So this is just, it's like some helpful information for you in case you need it. So your homework is going to be to do the 9.7 WebAssign. So good luck.